Greetings, ladies and gentlemen. Today we're looking at 5.4. We are going to look at different ways to interpret the definite integral. So let's get started. The notation for definite integral, as we have seen in the previous sections, we have, of course, the integral notation, and then going from A to B, where A is your lower bound and B is your upper bound of some function f of x with respect to dx. Okay. Now, when we look at application side, we also have to consider units. Okay. So the units for the whole integral, right? The units for this is equal to the units of f of x times the units of x, right? So it's the unit of f of x times the unit for x, right? Let's look at a quick example. Let's say f of x and x has same unit, like inches. Okay, then the integral of f of x from a to b will be has the unit of square inch, right? Something like that, right? Because it's inch times inch, square inch. So we can think about this as like an area. Now, of course, there can be some other things like this example we have here. Now, if R of t represents the rate at which the heart is pumping blood in liters per second, right? So let's keep that in mind. R of t is in liters per second. Okay. And time, t, is in seconds, right? T in seconds. Right, then the unit for the integral, right, going from 0 to 10, r of t dt, we'll have the unit of r of t times the unit for t. So that means it's going to be L liters per second times second, right? And then just like multiplying fractions, right, we can simplify the seconds in terms of units, and that will give us liters, right? So the units for this integral is in term of liter, right? And to be a little more specific, notice our lower bound and upper bound is from 0 to 10, right? So this L is the amount of blood pumped by heart between 0 and 10 seconds, right? As we can see right here. All right. Here is another way to look at the integral. So if f of t is a rate of change of a quantity like speed or growth rate or decay rate, then the integral from a to b of f of t dt is the total change in quantity between the lower bound and upper bound between time equal to a and b. All right, so here let's look at example 3 together. A man starts 50 miles away from his home and takes a trip in his car. He moves on a straight line, and his home lies on this straight line. His velocity is given in this graph. Okay, so let's look at this graph here. When the velocity is positive, it means he is traveling toward his home. When the velocity is negative, that means he's traveling away from his home. Okay, so essentially, we have a little cartoon to show what we are looking at here. So this man is 50 miles away from his home. If he is traveling towards the house, then we see that as a positive velocity. If he's traveling away from the house, then we consider that as a negative velocity. Okay, and we want to try to answer these two problems here, part A and B. A, when is the man closest to his home? Okay, so let's see. We started at 0 right here. And then from that point on, it's all positive. The slope is all positive until here, right? Well, velocity is positive, right? That means between time equal to 0 and time equal to 2, this man is traveling towards his house, right? And after our t equal to 2, the velocity is now negative. That means after 2 hours, he's going to turn the other way and start traveling. Right. So the time that this man is closest to the home is actually when t is equal to 2. Right. Closest to home at t equal to 2. Okay. Because between time equal to 0 and 2, velocity was positive. That means he was traveling towards his home for the first 2 hours. Now, it doesn't matter how fast he's traveling, right? As long as it's positive, as long as he is traveling towards his home. Now, part B, approximately how far away is he then, right? So here we're getting to the idea of definite integral, right? So the vertical, the function has unit of mph, right? This is, let's say, v of t. And then the horizontal, which is time, that is in terms of hours. Right, so when we multiply mph by hours, we get miles, right? That's the quantity we want. Okay, so to find miles, that's actually going to be the integral. That's unit for the integral going from a to b of v of t dt. Okay, so in this case, we actually want to take the integral of the velocity function to obtain the distance traveled between time equal to 0 and 2, because we're traveling towards his home. We want to find out how many miles was he away from the home at t equal to 2, since that's when he is closest to his home. All right, so the definition, or one way to find the integral, is by looking at the area under the curve, which means we want to approximate the area under the curve between t equal to 0 and t equal to 2, which is this area right here. Okay, distance traveled between t equal to 0 and 2. Okay, now of course there's no function. We can only estimate this by looking at the graph. So we're just gonna say it's about one box, or excuse me, or one grid box, right? So this area under the curve is about, so one grid box. So we can say that the integral going from 0 to 2 of v of t dt is about one grid box. All right, so one grid box will be like this, right? Which is a rectangle, easy to find. All right, so each box has the length of 30 multiplied by, so 30 mph multiplied by the width will be 1 hour, right? So that's about 30 miles. Okay, so for the travel between 0 and 2, time between 0 hour and 2 hours, this man traveled about 30 miles towards his house. Okay, so distance the man travels through the first 2 hours is the area under the curve between 0 and 2. This is what we found, this red area right here. The area corresponds to one grid box, or about the area of one grid box. Since each grid box has area of 30 miles per hour times 1 hour, which is 30 miles, the man travels about 30 miles towards home. So he is closest to home after 2 hours, and he is about 2 miles away at that time, right? So let's draw a picture about how the man is and how close is he after the 2 hours. Okay, so after 2 hours, at 2 hours mark, this man is about 20 miles away from his home, right? And that's the thing we're looking at right now, what we have in this case. Okay, so let's look at part B. When is the man farthest from his home? How far away is he then? All right, so we can go back to the graph here. So after the hour of 2, t equal to 2, between t equal to 2 and t equal to 5, um, the velocity is negative. It means this man is traveling away from his house after t equal to 2, and between t equal to 2 and t equal to 5 to be exact. Okay, so if he is traveling away from his house, then the longer he travels, the longer he's away from his home, right? So we're just gonna take the last one when t is equal to 5. That's where he is furthest away from home. And the distance traveled, just like part A, the distance that he traveled away from home will be the green area here. All right. And then we'll get into the details of how to approximate that as well. All right. So for part B, when is he the furthest away from home? It's going to be at hour 5 because he has been traveling away from the house between hour 2 and hour 5. And how far away is he? And that's something we have to work on by using some approximation about the area of the grid box here, right? So that's about 1, 2, 3, a little more than 3. Let's just say it's 3.5. Okay, so let's do that. Okay, so let's answer part B. When is the man furthest from home? Um, Furthest from home at t equal to 5, right? 5 hours after he has been traveling. And how far away is it? All right, so we want to find out what the area under the curve is. So this will be the distance traveled away from house. Okay, and this area, let's say it's about 3.5 grid boxes. Of course, this is just an approximation, and it will be a little hard to find the actual distance travel, but an approximation will do for now. Okay, all right. So distance travel away from the house, it's just like part A. We can represent this using a definite integral going from 2 to 5 v of t dt, which will also have the units in miles. Okay, so each grid box is about 30, so 3.5 grid box is going to be 3.5 times 30, which is going to be 90 91.5. No, 105. 105 miles. So after he stops and turn around, he traveled 105 miles away from the house. Okay, so let's draw a quick picture. So let's say he is now 20 miles from the house. And from t between 2, so this is t is 2. And from t equal to 5, he has now traveled 105 miles towards the other direction, away from the house. Okay, compared to when he was t equal to, compare where he was at time equal to 2. All right, so to answer that question, how what's the distance traveled? How far away is he then, right? So to figure out how far away he is, we just add a 105 and 20, and that is going to be 125 miles away from the house. Okay, and that's it. All right, the next type of application we're going to look at is the bioavailability of drugs. So this is a much technical terms in which I have absolutely no experience with, but I actually did some reading online. So let's look at a quick introduction. All right, so in pharmacology, the definite integral is used to define to or measure the overall exposure of a person to a drug during the course of treatment. This determines the bioavailability of the drug under different administration regimes. All right, so a quick definition for those of you who are in a bio or a medical field or who are looking into medical field. The definition of bioavailability refers to the extent a substance or drug becomes completely available to its intended biological destination, right? So let's say when we take a painkiller, right? How does our body absorb it, right? The does our body completely absorb it, or maybe not? Okay, so the exposure is equal to the definite integral starting with t equal to 0 to capital T sometime of the concentration function. Now we have seen the concentration function from last section from last chapter in chapter 4.8 when we talk about surge function. All right, so this is a picture of the surge function, right? We can see that after a few minutes, the concentration of the chemical in your bloodstream rise up rapidly and then decrease down slowly. So the area under this curve will represent your bioavailability. The higher the peak is, the more availability you have. And let's say if someone is not has a body that does not absorb the drug really well, maybe the surge function will look like this, which gives it a lower area under the curve of concentration, meaning that person will have a lower bioavailability. Now, in the context of um, the medical research, I have absolutely no idea what that means. But what I can show you is a view from the mathematical side. And hopefully, some of you can relate to this, and maybe this will help you in your future or when you're doing research or reading articles. Okay, so let's look at an example together. The concentration curves for a drug administered by two methods are shown in this figure, right? So we have method A and method B, and we can see that they are actually very different. And let's see if we can identify the differences between the two methods A and B in terms of their peaks, right? We see that method A actually reaches peak real fast and then it's higher than B. And in terms of the speed of absorption and total exposure. Right, so method A has a peak concentration about almost more than twice as the height of method B, right? So the peak here and on A is much higher than B, right? So let's say this is peak A and this is peak B. Right? It's much higher than the peak B, and then it also rises up to the peak much faster. Because method A achieves the peak concentration much faster than B, the drug is also absorbed more rapidly than in method A than method B. All right, so method A absorbs faster. Right, and probably absorbs more than method B as well, right? And method B and also method A provides greater total exposure to the drug. So meaning that we can look at the area under the curve, right? On the area under curve A versus the area under curve B, right? So from this case, we can say that method A also uh, has a greater exposure, right? Method A also has greater exposure, right? Remember that exposure is defined by the integral, the definite integral of concentration function, meaning it's represented by the area under the curve. Right? So method A has a greater exposure, meaning uh, it's going to be greater than the absorption or the exposure of method B. So if we can talk a little bit about this in another view, in the more of a biological view, right? The same type of drug can actually be enter your body in different form. For example, it can be taken orally, like you're taking a pill, or it can be injected into the blood, right? And from what I heard is that actually injecting your blood has a faster and higher effect, right? So in this case, we can probably think about method A as injecting some drug into our blood or into someone's blood, and method B would be taking that drug orally, like a pill or something, and it has takes a longer time to reach the peak, and then the concentration is not that great as well, compared to, of course, injecting that directly into your blood. All right, so um, it's just some things that we can look at and try to understand it from the biological view. But here we are just focusing on the mathematical view and try to understand this by looking at the graph. All right. And that'll be all for today. And thank you guys very much. I'll see you next time.